I wanted to do a short video to help explain when sequences go to 0 or when they go to a number, or what happens to the limit as n goes to infinity for a sequence. Now we've studied this, or you have studied this in calculus when it was x, when x was going to infinity, and we have nice smooth continuous functions. But now we can have ones that are discrete, that we just have this entity plus that entity plus this entity. But a lot of the same rules that we learned with functions will also work with sequences. So what I want to talk about is who goes fastest, who wins the race. Since we are only looking at limits that as n goes to infinity, we're going to concentrate on the speed. All of these are going to, well, that's not true, these don't grow. All of these from log on get bigger as n gets bigger. In terms of speed, though, the log functions go to infinity slower than power functions, and they go slower than exponentials, and they go slower than factorials. Even if this k were 1/2 and we had, if we had the square root graph, it's concave down, so it goes to infinity, but more slowly than, say, x squared. And the log function goes to infinity even slower, I can't draw with this cursor, even slower than the n to the 1/2 graph. Exponentials, they're speedy. Now this is assuming a is greater than 1. If a is less than 1, then you're really looking at something like 1/2 to the n, which means I have 2 to the n on the bottom. And the whole point of this is we're going to talk about what's on top, what's on bottom, who's going faster. So if you've got 1/2 on top, that's cheating. It's really on bottom. The fastest of all of these is of all the ones I'm listing, is in factorial. There's one more. See if I can do this. But I don't like playing with it, and we won't really see it with Taylor series. But if you've got n to the n, that's the speediest of the speedy. Let's see if I can erase this. Yay! Okay, so let's look at some things, some other possibilities. I don't have the cursor. Okay, so in general, who's faster? If the bottom is faster, you get 0. If the top is faster, you get infinity. If they're kind of the same rate, you're going to get some constant, non-zero constant. And what I mean by the same rate, the only time this happens, as far as we will see in this class, is if you have polynomial type things. The degree of the top is the same as the degree of the bottom. And you'll see why I'm wavering on that polynomial type thing in a second. So let's look at some examples. So up here we have limit as n goes to infinity of 5n squared minus 3n minus 9 over n cubed plus 6. Now when you are doing this, you look at the top and you go, that's way too fat. This is all I care about. Let's see if I can make this line smaller. Looking at this expression, on top, the only thing we care about is 5n squared. Because as n goes to infinity, it's going to leave this crap in the dust. Negative 3n minus 9 is just kibble. Doesn't matter. The 5n squared is what's going to drive the top. Same thing on the bottom. I look for the highest degree. That's n cubed. And the 6 is just noise. So this is really 5n squared over n cubed. The degree of the bottom is 3, the degree of the top is 2, the bottom is faster, so this is going to give me a big old honkin' 0. Sorry about the bad handwriting. Okay, let's try another one. Let's look at this one. So on this one, we have 2n plus 5 over 3n minus 2. Again, plus 5 and the 2 is just noise. This is all I care about. 2n over 3n. And the n's actual will cancel if you're thinking about it that way, because that's what's driving it. So the answer to this will be 2/3. Because they're going at about the same rate. Okay. Let's look at a different one. Now this is what I mean by it's kind of a polynomial, but no, it's really not a polynomial, but I'm going to call it a polynomial anyway because it makes our life easier. Notice here on top we have the square root of 9n squared. So the square root of 9n squared is all that's is the important thing on top. Again, this shit's noise. On the bottom, all we have is 4n. Now, simplifying it, 9n squared is 3n, absolute value of n, but we're going to positive infinity, so that's fine, over 4n. The n's cancel. Wow, my penmanship sucks. So this limit is 4 3/4. So these two, they go at about the same rate, so you're looking at their leading coefficients. You're looking at, because the n part's going to cancel out, so all that you're left with is the 2 on top and the 3 on the bottom, or here the 3 and the 4. Okay, let's do this one. Okay, so here we have the limit as n goes to infinity of n factorial plus 3 to the n over 5 to the n plus n squared. If I look at the bottom, n squared is really slow compared to 5 to the n. So this is the one I care about on the bottom. This is noise. On top, well, now we have an exponential, but we have factorial. Factorial wins. This guy is lost in the dust. So I've got n factorial on top, 5 to the n on the bottom. N factorial is the fastest, so this will be infinity. Let me do one more. Okay, here I have 2 to the x on top, that's all I have, and a 5 to the n on the bottom. 2 to the x is faster. This is infinity. So what you want to do is when you have a ratio of two functions, you want to look at who is the fastest on top and who is the fastest on bottom. Compare the two to see if the top is faster, you get infinity. If the bottom is faster, you get 0. Yeah, if the bottom is faster, you get a 0. And if they're about the same, which means they have polynomial-like properties, then you're going to get a ratio of the top leading coefficient and the bottom coefficient. If you need more examples, let me know. I can type a ton of these up for you.